Hello all. So in this video I am going to explain one more application of the Gauss law. When Gauss law is applied to uniformly charged sphere, what is electric flux density and electric field intensity in different region of the sphere. So uniformly charged sphere means in previous case we saw the charge lies only on the outer surface of the sphere. So here the charge completely lies completely inside of the sphere. So I am considering a sphere of radius a, and the sphere has a radius a. In the sphere, inside of this sphere, the charge is completely distributed, okay, the uniformly distributed, and the volume. If you take this sphere, this is a volume. So the volume charge density of this sphere is taken as rho v. The volume charge density of this sphere is taken as rho v. So same as previous case, here also we are going to consider three cases. So when point lies outside of the sphere, when point lies on the sphere, and when point lies inside the sphere. Now first case I am considering when point lies outside the sphere. So here if you take the Gaussian surface which is joining this point P, which is having a radius of r, the Gaussian surface having a radius of r. So as shown in the figure here, the dotted line circle shows the Gaussian surface. On that Gaussian sphere, I am considering a small elemental area ds. So I am considering a small elemental area ds at the point P. So it is perpendicular to the radius line, the line joining between the point and line, which is perpendicular. This ds is perpendicular to that line. So the component, which is the vector component which is normal to this surface area ds, is the vector which is along with the direction, the radial direction, that is ar cap. Similarly, the electric flux density also in the direction of the radius, the electric field flux density also in the direction of the radius. So d is given by dr into ar cap because it is along the radius. So dr is a radial component into ar cap. So we can write in a sphere the surface normal to radial axis can be written as r square sine theta d phi. So according to Gauss law, d psi is equal to d dot ds. So I can write dr into ar cap. So between d and ds can be written as r square sine theta d phi into ar cap. If you take dot product of these two, you will get dr r square sine theta d phi, because ar cap dot ar cap will be 1. So this is d psi. Now I have to find what is psi. How to find psi? Psi can be obtained by taking surface integration of this quantity. So surface integration of d dot ds will be equal to psi, which is equal to charge. So if I integrate this, so I can write the psi which is equal to q, which is equal to surface integration of d dot ds. So here we are going to do double integration with respect to theta and phi. So limit for phi will be 0 to 2 pi and theta will be from 0 to pi. So integration of dr r square sine theta d phi. So if you integrate and simplify this, you will get q is equal to dr r square 4 pi. So q is equal to dr r square 4 pi. So rearranging this equation in terms of dr, I will get dr is equal to q by 4 pi r square into ar cap coulomb per meter square. So I got what is electric flux density. Now I have to obtain what is electric field intensity. The relation between electric flux density and electric field intensity is d is equal to E is equal to d by epsilon naught. So substituting this d in this equation, I'll get q by 4 pi epsilon naught r square into ar cap, which is equal to vector E. So that is electric field intensity. Now we know that this sphere consists of the uniformly distributed charge. So this is a volume. So I am considering the volume charge density of rho v. So I can obtain q from this rho v by volume integrating rho v with respect to volume. So So I can write Q is equal to volume integration of rho V into dV. Rho V into dV. So volume integration means there will be triple integration. So one is with respect to theta, other one is with respect to phi, and one more is with respect to r. Because spherical coordinates, we have three coordinates r, theta, and d phi. So in volume integration, the one integration with respect to phi, other integration with respect to theta, and one more integration with respect to r. So limit for r will be from 0 to a, depends on the radius of Gaussian, radius of the sphere here 0 to a. Similarly, for theta it is 0 to pi, and phi it is 0 to 2 pi. So integrating rho v into dv for spherical coordinate system is r square sine theta dr d theta d phi. Now integrating this, you will get this one. Then simplifying this, you will get 4 by 3 into pi a cube rho v coulomb. So now we know that E is equal to Q by 4 pi epsilon naught r square. So in this equation, substitute Q is equal to 4 by 3 pi a cube rho v. In this equation, you will get E is equal to, after substituting this in this equation, you will get E is equal to a cube rho v divided by 3 epsilon naught r square into a r cap. This is the expression for electric field intensity when the point lies outside of the uniformly charged sphere. Now D can be obtained as epsilon naught into E, so I can write a cube rho v divided by 3r square into a r cap. Though this is the expression for D when point lies outside the uniformly charged sphere. Next case, we will see when point lies on the sphere, what happens. So we know that expression for E when it lies outside the sphere, that is E is equal to a cube rho v by 3 epsilon naught r square. Here r is equal to a, so it can be written as a cube rho v by 3 epsilon naught a square into a r cap. So this simply, after simplifying this, I will write rho v a by 3 epsilon naught. Using this equation, I am writing here this equation. So instead of r, here I am writing a, because here Gaussian surface radius also equal to radius of the sphere. So it can be rho v a by 3 epsilon naught into a r cap. Now I can obtain d as epsilon naught into e, so the equation will become rho v into a by 3 into a r cap. So this is second case. In third case, I am considering the point lies inside the uniformly charged sphere, then r is less than a. Radius of the Gaussian surface will be less than a. So this will be the diagram for that. Here also I am considering a small surface area of a inside the sphere. Here the charges, whatever charges present outside of the Gaussian surface, no need to consider, because so as per Gauss law, it won't affect the flux lines produced from that surface. The flux lines only affected by charge present inside the sphere. So I have to consider what is the charge present in the inside the sphere. Here I am considering a small element area ds, which is normal to radius. Similarly, I am considering the d, so which is in the direction of the radius, so it is dr into a r cap. So I can write d is equal to dr into a r cap, and ds is equal to r square sine theta d theta d phi into a r cap. If I take dot product between d dot ds, I will get d psi is equal to dr into r square sine theta d theta d phi. Now I have to find what is psi by integrating this over the limit of 0 to 2 pi for phi and 0 to pi for theta. So I will get q is equal to 4 pi r square into dr. Then I rearranging this equation, I will write dr is equal to q by 4 pi r square. Now I can write d is equal to q by 4 pi r square into AR cap, right? So I know what is Q here. So Q is equal to surface integration of rho v dv 0 to 2 pi 0 to, if I integrate this, I'll get this equation. So I'll get this equation as per same as case 1, it is 4 by 3 pi r cube into rho v. Here you can observe here, in case 1 we have taken limit from 0 to a, but here we took limit from 0 to r, because as I told earlier, we are considering whatever charge present in the inside of Gaussian surface only, not the charge present in the whole sphere. We are considering only charge present inside of the Gaussian surface. That's why limit is from 0 to r here. For limit is from 0 to r. So substituting this and integrating this, you will get 4 by 3 pi r cube into rho v. Now if I substitute this q in this equation, I will get d is equal to r by 3 into rho v into ar cap. So d is equal to r by 3 into rho v into ar cap. Now to obtain electric field intensity, you know that E is equal to d by epsilon naught. So I can write that if I substitute here d as r by 3 rho v, so I will get r by 3 epsilon naught rho v into ar cap. This is the expression for electric flux density and electric field intensity in a uniformly charged sphere when point lies in the inside of the sphere. So we got all the three cases. For first case we obtain expression for d as a cube rho v by 3 r square into ar cap, and E is equal to a cube rho v divided by 3 epsilon naught r square into ar cap. In second case, we got expression for d as rho v a by 3 ar cap, and expression for E as rho v a by 3 epsilon naught into ar cap. And for third case, we obtained expression for d as rho r by 3 into rho v ar cap, and expression for E as r by 3 epsilon naught rho v into ar cap. For the point lies inside the sphere, uniformly charged sphere. This is the expression for d and E. Now if you see the variation of the electric field intensity with respect to radius of the Gaussian surface, so from till the sphere, when the radius of the Gaussian surface is equal to radius of the sphere, the electric field intensity increases linearly. Electric field intensity increases linearly. If you observe here, it is increases linearly. Once it reaches to outer surface, then it starts to decay in exponential manner. So it is when the radius increases, the electric field intensity starts to decrease in exponential manner. So this is how in a uniformly charged sphere electric field intensity varies from point to point. So this is one more application of the Gauss law. So we saw different applications of the Gauss law in series of videos. So in next video, I am going to share how the Maxwell's first equation can be derived, and later we can see what is divergence theorem. Thank you.